Hi everyone. In this module, we're going to talk about the chi-squared test, which is a test that we typically use when we're interested in associations that involve nominal or ordinal variables. Okay, so I'm going to start by doing a brief introduction to nonparametric tests. And then we're going to talk about two different types of chi-squared test, the goodness of fit test and the chi-squared test of independence. So up until this point, what we've mostly talked about in this course are parametric tests. These are tests that we typically use with those interval or ratio level dependent variables. So those are the variables that are quantitative variables that you can calculate means for. And usually with all of those tests, we talk about assumptions. So we may talk about the fact that we want our dependent variable to follow a normal distribution. We have all kinds of rules about when we cannot use parametric tests. Non-parametric tests are a little different though. So non-parametric tests don't have all those assumptions about sort of the shape of the population. And the other thing that's important about them is that we typically use these for nominal or ordinal level dependent variables. So these are going to be the variables that have categories. So things like what color are your eyes is an example of a nominal variable. Or an ordinal variable if we're putting things in order, but they're still categories. So if I ask about level of education, and the options are high school graduate, some college, bachelor's degree, master's degree, doctoral degree. Those are categories, but again, those categories have an order to them. And so the non-parametric tests that we're going to talk about today are really going to be focused on these nominal or ordinal level dependent variables. These aren't as powerful as the parametric tests that we've done so far, but we very much use these in statistical analysis. And so the two tests we'll talk about today are the chi-square goodness of fit test and the chi-square test of independence. All right, so the first test is the chi-square goodness of fit test. And this is a single sample test. Usually what we're doing is we have a distribution of some kind of categorical variable, and we're comparing it to some known population value. And so you'll see people use the Greek letter chi to write out chi squared. And then sometimes see people write goodness of fit as GOF. So again, it's a single sample test. We're comparing the results in a sample that involves a categorical variable to a known population value. All right, let's look at an example. So let's say we're doing a research study on traffic tickets, and we want to know if um, teenagers get more tickets than adults. And so to answer this question, um, we take a random sample of traffic tickets each month for a year in a particular area. And let's say in total we get 72 tickets. So we get a random sample of 72 tickets that were given within a given year. And then we look at those tickets, we find that 11 of them went to teen drivers and 61 of them went to adults. And so that's what we see here in this table. So 72 tickets total. We have 11 in the teenage category and 61 in the adult category. All right, and so then after that, we want to know whether or not that sample lines up with what's expected in the population. And so what we do is we get data from the Department of Motor Vehicles. In Michigan, it would be the Secretary of State. And we find out that about 8% of licensed drivers in this town are teenagers. And so we want to know if teenagers are getting more than their fair share of traffic tickets. So if we know that 8% of drivers are teenagers, we would expect that 8% of tickets would go to teenagers. And so if we actually look at the data that we just collected, however, we see that teenagers actually got more than 15% of the tickets. And so what we're trying to figure out is, do the teens get more than their fair share of traffic tickets? Um, or are we just seeing sampling error? Is that 15% within the confidence interval that we would expect for 8%? And so that's what we're trying to figure out. Is there a statistically significant difference between um, the proportion of teens who get tickets, and the percentage of drivers in town. All right, so now it's time for us to do our hypothesis testing. So we start off by picking our test, check our assumptions, come up with our null and alternative hypotheses. We set our decision rule, which usually involves calculating some kind of critical value. And then we compare that critical value to some test statistic, which helps us to decide whether or not to reject the null hypothesis. And then from there, we interpret our results. So this is the same process that we've done all semester, and we'll continue to do it here. Okay, so first we're picking our test. And we know we want to do a single sample test because we have a sample value of about 15.28%. That's the percentage of teenagers who got our tickets in our sample. And we're comparing that to a specific value of 8%. That 8% corresponds to the percentage of all drivers that are teenagers. And our dependent variable is a nominal level variable. It's categorical. We have who gets a ticket, and our two categories are teen or adult. And so if we want to do a test like that, that corresponds to the chi-square goodness of fit test. Okay, so step two, we check our assumptions. And so there's three assumptions in the chi-square goodness of fit test. First, data come from a random sample, similar to what we've already talked about in previous tests. Second, we have independence of observations. So we're not talking about any sort of paired samples in this example. And then finally, our expected frequencies. We must have at least 5 observations per cell. And I'll talk about that a little bit next. And so let's assume that all of our assumptions are in effect here and none of them are violated. You may wonder what I mean when I talk about expected frequencies. Typically, when we look at this nominal categorical data, we often look at it in what are called contingency tables or 2x2 tables. And we call them 2x2 tables because usually you have two categories for your independent variable, in this case, age group, teenagers versus adults. And then you usually have two categories for your dependent variable, in this case, ticketed or not ticketed. And so within those tables, you usually have 4 cells, which I've labeled here as A, B, C, and D. So cell A would be the people who are teenagers that got tickets. Cell B would be teenagers who did not get tickets. Cell C would be adults who got tickets. And then cell D would be adults who did not get tickets. And so when we talk about um, 5 cases per cell, that's what we mean. In each of these cells, A through D, we want to have at least 5 cases or 5 observations in order to use the chi-square goodness of fit test. All right, step 3, we want to talk about our hypotheses. So the null hypothesis would say that there's no difference in the proportion of teens who get tickets in the sample compared to the proportion of teen drivers in the population. So in other words, the percentage of tickets received by teens is 8%. It's not any different than what the proportion is. The null hypothesis would say that there is a difference. So it would say the proportion of teens who get tickets in our sample is different from the proportion of teen drivers in the population. So you'll notice when you're talking about sort of these nominal or ordinal variables, we're not talking about means here. We're talking about proportions, or you can think about them as percentages as well. Proportion and percentages are similar. But that's important to distinguish because when we have interval or ratio dependent variables, we're talking about differences in means. When we're talking about nominal or ordinal variables, we're talking about differences in proportions. All right, so we have our hypotheses. Now we're on to step 4, which should be familiar. Now it's time to set our decision rule. And so to set the decision rule, we need to come up with a critical value. Here it's going to be the critical value of chi-squared. And this value determines whether or not we reject the null hypothesis. And so in your textbook, there's an appendix table 9 that we use to find the critical value of chi-squared. And so to get that critical value, there are 2 pieces of information you need. One, we need to know how willing we are to make a type 1 error. So that's our alpha level. And then we need to know the degrees of freedom the test has based on the number of categories. All right, so How many degrees of freedom do we have? So when we're talking about degrees of freedom here, we're talking about degrees of freedom for our independent variable. So our independent variable here is age group, and the categories are teens and adults. So our degrees of freedom is going to be equal to k minus 1, where k is the number of categories for that independent variable. So here we have two categories, teens and adults. So our degrees of freedom is going to be equal to k minus 1, which is going to be 2 minus 1, which is just 1. And so we can use appendix table 9 to find the critical value for our chi-squared. All right, so here's an example of this table. There's a full table in the back of your textbook, appendix table 9. But let's use alpha level 0.05, which is what is the most commonly used alpha level. And then we said our degrees of freedom was equal to 1. So we look at where those two intersect, and we get 3.841. And so that's the critical value of chi-squared. And that is the value that we're going to compare to our test statistic to decide whether or not to reject the null hypothesis. All right, so if chi-squared, if our critical value is here at 3.841. And so that's the cutoff for the common versus the rear zone. And so if we come up with our test statistic, which we'll do in a second, if our test statistic is out here in the rear zone, that means we're going to reject that null hypothesis. If our test statistic is over here, that means we will not reject the null hypothesis. All right, so now it's time to calculate the test statistic. And in calculating the test statistic, what we want to do is compare the observed frequency of each category of the dependent variable, which we'll call F observed, to what frequency we would expect if the null hypothesis were true. And that's what we would call F expected. So we already know the observed frequency, right? We know that when we look at the distribution of tickets, we found that 11 of them occurred in teenagers and 61 of them occurred in adults. And so that's our observed frequency, and we want to compare that to an expected frequency. Let's look at how we would use this formula. So let's say we're interested in calculating the expected frequency of traffic tickets for teenagers if the null hypothesis were true. So we know from the Department of Motor Vehicle records that 8% of drivers are teenagers. So we would expect that 8% of traffic tickets would go to teenagers as well. And so we know we had a total sample size of 72. And so we would expect 8% of those 72 tickets to go to teenagers. So we would take our sample size of 82 and multiply that by our proportion expressed as a decimal. So here it would be 0.08, that's the same as 8%. And so we multiply 0.08 times 72 and we get 5.76. So we would expect to have 5.76 tickets among teenagers if the null hypothesis were true. Now let's look at adults. So we know that 92% of drivers are adults, and so we would expect that 92% of tickets would go to adults. And so we know again there's a total of 72 tickets in our sample. And so if we take that sample size of 72 and multiply it by the proportion expected, which here would be 0.92, we get 0.92 times 72, and that would be 66.24. So if the null hypothesis were true, we would expect that 66.24 of the tickets received would go to adults. All right, so let's review our data again. So our observed frequency of the 72 tickets that we took a sample of, we found that 11 of them went to teenagers and 61 of them went to adults. When we calculated the expected frequency, we found that we expect, if the null hypothesis is true, we expect that only 5.76 tickets should go to teenagers and 66.24 tickets should go to adults. If you notice, if you add these up, you should get the same value as the sample size. If you don't, then perhaps you did something wrong with your math. Okay, so now that we know the observed frequency and the expected frequency for both of our categories, we can now calculate the chi-squared test statistic. And so the chi-squared test statistic is going to be the sum of the observed frequency minus the expected frequency squared divided by um, the expected frequency. And we're going to sum these up for each category. And I'll show you an example next. All right, so now let's calculate our chi-squared test statistic using the formula that I've given you. So remember, we have our observed frequencies here for both teenagers and adults, and then we have our expected frequencies here for teenagers and adults. And we'll need all of these values to compute our test statistic chi-squared. All right, so the first step, we have here on our equation, the left side is going to correspond to teenagers, the right side corresponds to adults. So we're going to sum up um, these values for both the teenagers and the adults to get our chi-squared. So for each cell category, we're going to subtract the expected frequency from the observed frequency. And again, these are our adults and our teens are our categories. So for teens, our observed frequency is 11. Our expected frequency is 5.76. And then we do the same thing for our adults. So our observed frequency is 61. Our expected frequency is 66.24. And then from there, we'll square each difference. So we'll just put a square sign here to remind us we're supposed to square both of these. And then we're going to divide each squared difference by the respected expected frequency to get a quotient. And so here we're going to divide the teenagers by 5.76, which is expected. And then we're going to divide the adults by 66.24, which is what is expected for the adults. All right, so then we do all this math. We're going to get, if we take 11 minus 5.76, we're going to get 5.240. If we take 61 minus 66.24, we're going to get negative 5.24. We're going to square both of those. Keep in mind, we still have our denominator. We'll work with that in a second. So we'll square each of these. So 5.24 squared is going to give us this 27.45 number. Negative 5.24 squared is going to give us this 27.45 number here. Now we have both of our denominators, and so now we're going to solve for each of those. So 27.45 divided by 5.76 is going to give us this 4.76 number. 27.45 divided by 66.24 is going to give us this 0.4145 number. We add these up, and we're going to get 5.1814. We're going to round to 2 decimal places to get 5.18. So our chi-squared test statistic final answer is going to be 5.18. All right, so now what do we do with that? So if you remember, we said our critical value of chi-squared was 3.841, and we compare that to our chi-squared test statistic. And remember, we said that if the test statistic is greater than our critical value, we know that that test statistic is in the rare zone, and so we reject the null. If it's less than that critical value, then we know it's in the common zone, and so we will not reject the null. So here we have a test statistic of 5.18, which is going to be out here somewhere. And so that's clearly in the rare zone. And so that tells us that we are going to reject the null hypothesis because our test statistic chi-squared is greater than our critical value of chi-squared. All right, so our main interpretation at this point is going to be, was the null hypothesis rejected? And we said yes, because our critical value of a chi-squared was a smaller number than our test statistic chi-squared. So our test statistic was in the rare zone. And so that means that we do reject the null hypothesis. Okay, so now let's put our results in APA format. So first we have the chi-squared, and it tells us that we're doing a chi-squared test. The 1 in parentheses tells us the degrees of freedom. Remember, the degrees of freedom is the number of categories for our independent variable minus 1. The n equals 72 tells us the sample size. The 5.18 is the test statistic that we calculated. Remember, it should have 2 decimal places. 0.05 is our alpha level. And if we say P less than 0.05, that lets us know that the null hypothesis was rejected. And so we have a less than 5% chance of rejecting the null hypothesis when in fact the null hypothesis was true. All right, so now we want to know the direction of our results. So we're going to compare what was observed to what was expected. So because teenagers make up 8% of drivers, we expected that they would receive 8% of tickets, but we actually found that they got 15.28% of tickets. And so because we only have two categories, it's actually easy to tell the direction of the difference. And so we can say, based on what we found, that 15.28% actually is statistically higher than 8%. So we can conclude that teens in this town get significantly more tickets than expected based on the number of teams who are drivers.